equivalence in quantum rings and invariance in knots. So take it away.
Thank you. Okay, hello everyone. Most of you know me. So my name is Dipali Swain. I'm a PhD student, fourth year from University of South Florida. And today we are going to talk about quantals and its uses in knot theory. So generally speaking, quantal is an algebraic structure, but it comes from the three Reidemeister moves that we know in knots. So I'll try to jump into that. So at first we'll talk about a bit of knot theory and motivation of quantals. So where does the notion of quantals comes from? So essentially what I deal with is low-dimensional topology. So low-dimensional topology is a space where you study about small dimensions and you look at their properties. And a knot is basically an image. It's an image of a smooth embedding of S1 in R3. For those of you, if you don't know what a smooth embedding is basically it's a injective map that you basically take the S1 and you just put it inside R3 and you look at it. And then we try to study about it. So we take various types of embeddings and all those results in different types of knots. So as you can see in here, clearly you can see a knot. This is known as a trefoil, which has three crossings. And an equivalent image of the trefoil can be seen in a similar manner. They come out from two different embeddings, but they give out the same knot. Now comes the Reidemeister theorem. So Reidemeister proposed this theorem. Knots are invariant under three Reidemeister moves. So essentially what you do is that you take a knot, remove its isotopy from R3. When I talk about isotopy, it's like what are the similarities, you know. It is doing that is same as taking the shadow of a knot. If you take a shadow of a knot, because you are in R3, the shadow is going to be something in R2. A knot is basically something in R2. You look at that and remove all the three Reidemeister moves. It is still the same. So basically what I'm doing is I'm going a dimension lower so that I'm able to see things. So I can basically draw them. So when I jump into Reidemeister moves, these are the three Reidemeister moves. So basically what it tells me that if I'm on R2 and I have, say, if you have a string, you just take and then just go around it. Essentially it's the same as you just elongate it again, back to string. Similar thing happens with two sets of strings. If you have two sets of strings, one string overlapping on the other string completely, you can basically pick the string up, put it this side, and you still have two parallel strings. And a similar thing happens with the Reidemeister third move, which has three strings involved. It's the same thing. You see, you'll have something like one string going all the way over on two other strings, and there's one more string which is going all the way over to the third string. You can just permute them and you again end up with such a diagram, and they all are equivalent. Now, we talk about something called when do you say two knots are same? Because we are trying to see difference between knots. So when do you say two knots are same? Well, two knots, say K1 and K2, are said to be equivalent if I continuously deform my K1 and obtain K2. Now this continuous deformation is basically taking the Reidemeister moves into account. So I take any knot, I keep respecting the Reidemeister move when I'm removing, like when you're lifting up a string and putting it on left or the right, assuming like you're taking the Reidemeister move 1 or Reidemeister 2 or the third, you essentially come up with the same knot, or if you can unknot it. So what you're trying to do is that if you take this one knot and you keep doing that and you get another knot, they both are said to be equivalent. So as long as they're respecting the Reidemeister moves, they are still equivalent. One example here that you can see is this one that looks like a knot, but when you keep doing the Reidemeister move, so the first one what I did was I did a Reidemeister 3 move, and then I see the knot now looks like this. Now with the Reidemeister 1, which removes the self loop on the right, it turns into a straight, and then I do another Reidemeister 2 move and it turns into an unknot. So essentially those two knots are the same. It's basically an unknot here. That is equivalent to this. Based on this diagrammatic view, we basically develop algebra over it because we want to do things algebraically. Now we define a set or like an algebraic structure called a rank. So we take a set X We define a binary operation on it. What is the binary operation? Following certain rules. So the first rule is that the operation from y going towards some y, you give this a triangle. You can give any symbol you want. But yeah, this map should be basically bijective. So this tells that the right multiplication is bijective, multiplication by right. The second one tells the right distributivity. So if you have something multiplied from the right hand side, it distributes over the things on the left side. As you can see, you have x times y and then times z. Then z just distributes over x and y. Now, this structure becomes a quandle if it takes idempotency into account. Meaning, if I take an element and act itself over it, I should get the element back. Taking all three of them, it basically forms a quandle. I define a rule in order to take it to back to not theta. What I do is I define this operation. I call that as a positive crossing. If you see y is over x, so essentially you can just take it from your right hand. So this thing basically is crossing over your thumb. That's how you see it. So when the one facing towards the left is crossing over the one towards the right, because it is going all the way down, so it starts from y, ends at y. But the moment you go under y, it takes the operation into account. It admits the operation, so that basically becomes x triangle y. Because x goes under y. So this essentially tells that. Well, then there's another possibility that this now you have x here and then you have y here. Well, this dude can go above this dude. The moment that happens, it admits the reverse crossing. So I call this as a negative crossing for myself. Okay? So that is known as a positive crossing. This is known as a negative crossing. The easiest way is take your right hand, place it like this. This side facing, and your thumb basically goes under your palm. That's how you see it. That will be a positive crossing, likewise this side will be a negative crossing. So if you want to know whether a crossing is positive or negative, just place your right palm and check. Now, what I can do is, using Readmaster moves, I can look at the axiom of quandles being satisfied. Look at the Readmaster move 1. Well, x admits x within itself. You take the string x, start all the way, act over itself, you get x star x. Basically, this is equal to x. That's what the Readmaster move 1 is saying. What is Readmaster 2 saying? Readmaster 2 tells me that I have a string y, and now x is going under y. So I'm trying to define the existence of multiplication by right. So multiplication by right, and also trying to prove that it is a bijection. So what I'm doing is, I take my y, I act x under y. So the moment it goes under y, it becomes x triangle y. Now this x triangle y goes all the way under y again. So what happens? We'll have x triangle y, but now this is a negative crossing. So it will take inverse, the inverse crossing times y. That basically gives you x triangle y. This tells you that this kind of operation is right multiplication bijective. Likewise, the third one admits the distributivity, the right distributivity. The diagram should be self-explanatory. You start with two strings x and y, x going under y, so the moment it reaches here, I'm an x triangle y. The moment it reaches here, because this is z and this dude is going under z, so it becomes x triangle y, triangle z. Z comes down as z because it is going all the way above everything else. Y comes over x, so it's still y, but the moment it goes under x, it goes under z, it becomes y triangle z. And Readmaster 3 tells me, Readmaster move 3rd tells me that these two diagrams are same, so obviously this operation right at the right hand side, the most right hand side, that is x triangle y, O triangle z, is basically x triangle z, triangle, y triangle z. And this is essentially your right distributivity. Now, since we have the structured quandle, we want to look at some examples. One of the very easy examples is taking the group z modulo 3z and take the operation as x triangle y as 2y minus x. So whenever I get two numbers, say 1 and 2, I take number 1 and number 2. And remember, quandles are non-commutative. Naturally, they are non-commutative, which means when you operate 1 over 2 and you operate 2 over 1, you're going to get two different results. Now here, luckily it just happens that they get the same result, but that's fine. So you get 2y minus x. The Cayley table of such a quandle will look something like this. and this kind of quandle is essentially known as the dihedral quandle. So a generic dihedral quandle, a general dihedral quandle, which is represented by Rn, will be given by x triangle y equals 2y minus x, where both x and y come from z mod and z. Another example here is over z mod 7, and the operation here I'm taking is 3x plus 5y over mod 7. The Cayley table is going to look something like this. Now, what we do is we associate some algebra over quandles. So like you know about groups, you can associate algebra over groups, as in you take a group, take a ring, associate this ring over this group. What comes out is a group ring. Every element is going to look like a polynomial inside. That is something similar I do with quandle rings. What I do is I take a quandle x, I take an integral domain with unity, that is k, and I associate this with my quandle. I call that as k of x. This is going to admit some formal definitions because it forms a quandle ring, so it's going to take the ring structure. A typical element is going to look like alpha x times e of x, where e of x is an element from the quandle, alpha x comes from the integral domain k. Addition is simply pointwise, but the multiplication, the moment you get into multiplication, so you take one element, you take the other element, the moment you multiply, the integral domain elements multiply normally, but here, now it starts respecting the quandle multiplication. Unlike group rings, where the most basic structures or like the most natural occurring structures are units, in a quandle ring, the most naturally occurring structure would be an idempotent. Because the first axiom of quandle essentially tells you about idempotency. That is, x times x is basically x. So anything that you pick from a quandle ring is always going to have a natural structure of self-idempotency. So I talk about idempotence of quandle ring. So what I do is, given a quandle and an associated quandle ring, I can look at a non-zero element said to be as an idempotent if it takes idempotency, that is u squared equals u. Now from this definition, one can clearly see that any element inside a quandle is itself a self-idempotent. And those kind of idempotents in my quandle ring are going to be called as the trivial idempotents. So a quandle sits inside a quandle ring. Every element inside a quandle is an idempotent. This also sits inside the quandle ring, but these kind of idempotents, I just call them as trivial idempotents. My job is to look for non-trivial idempotents. Things that look like, say, alpha E1 plus alpha E2 plus alpha E3, like alpha E1 plus beta E2 plus gamma E3. But I want to see what kind of, is this an idempotent or not? So I clearly want to see some non-trivial idempotents, because trivial idempotents I always have. I just pick elements from the quandle and I'm done. So for example, if you consider the quandle R3, that is the dihedral group of order 3, then over the ring Z is an integral domain as well. So over the ring, no, Z is not an integral domain, my bad. Z is a ring, so you have over this ring, you have alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3. This element itself is going to look like a general element in Z of R3. But when you take the idempotent set for this one, it's only going to be trivial idempotents. It's just R3 itself. Clearly R3 is going to be a quandle in itself, but this doesn't always happen. For example, if I change my ring, take the same R3, but change your ring to say Z modulo 2. When you take Z modulo 2, the set of idempotents are basically this, but they do not form a quandle within themselves. A counterexample to that is basically you take E1 plus E2 times E1 plus E2 plus E3. The multiplication is not closed because you get 0, and 0 is not an idempotent element. There was a conjecture given by Kaplinsky, which is known as the Kaplinsky's idempotent conjecture. That was for group rings. But in 2020, mathematicians Bardakov, Singh and Passy rose a question about, like, they basically tried to draw an analogy from Kaplinsky's conjecture for group rings to Kaplinsky's, like, if they could find a conjecture, a similar conjecture in quantum rings. Kaplinsky's conjecture for idempotence was that if you have a torsion-free group and a field F, then this kind of group ring will have no non-trivial idempotent, meaning every idempotent is going to be trivial. Now they Bardakov, Passy and Singh basically brought up an analogy in quandle. Their analogy for quandle rings was that if I have two quandle rings isomorphic to each other, what can I tell about the quandles? Will they also be isomorphic? Isomorphic as in, if they are structurally same, does that mean that the quandles will also have the same structure? Turns out the answer is no. I have an example here. This is what we do is we take two quandles, x and y. We take the field of characteristic 3. For ease, you can just take z modulo 3z. This map phi is basically isomorphism between these two quandle rings. But if you look at the first row of x and the first row of y, then they both are not same symbolically. Meaning, symbolically these two are same and these two are same. But here if you see, these two are same, this is different, and again this one is same to the third one, the second one or the first one. So essentially this is like 1, 1, 2, 1. The last one is 1, 1, 2, 2. So these two quandles are not same because they do not admit the same kind of structure. So this kind of disproves the part that having having quandle rings with the same structure does not imply that quandles should also have the same structure. Now, we started developing more, so my advisor Anam Dadi and me and Dr. Singh, when he visited to USF, we started working on this more, and this is how research works. We are trying to look at the conjecture, but we just stumbled upon some more results. So we were still not able to prove the conjecture in general, but we could stumble upon some more results. One of them was this, because I'm trying to study non-trivial idempotence. So I want a family of quandle rings which gives me non-trivial idempotence, and also I want a family of quandle rings which gives me only trivial idempotence. When I did that, I came across this proposition which tells that if you have X a quandle which contains a subquandle whose order is more than 1, then this K of X is, this quandle ring K of X will definitely have non-trivial idempotence. The proof is fairly straightforward. It's just a combinatorial problem. You essentially just count the number of elements and you come to see that essentially this has a non-trivial idempotent. One very specific example is the first connected quandle of order 6. This has a trivial subquandle of the form 1, 2, 3, 4, 5, 6, which means basically 1 star 1 is 1, 1 star 2 is 1, 2 star 1 is 1, 2 star 2 is 2, and 2 star 1 is also 2. So those kind of structure. And your non-trivial, the first non-trivial idempotent will be of this form. Alpha times T1 plus 1 minus alpha times T2. This is the first non-trivial idempotent. Similar thing can be done with E3 and E4 and E5 and E6. And these are examples of non-trivial idempotent in the first connected quandle of order 6. We obviously did some more computer experiments in our paper that we recently submitted, and we made the following conjecture, which is analogous to Kaplanowski's conjecture, and our conjecture is the following. An integral quandle ring, meaning my associated ring should be an integral domain. So I take my associated ring as an integral domain and I put a quandle inside, so forming a quandle ring of a semi-Latin quandle, but my quandle is also separate, is also of a special kind. It's a semi-Latin quandle, it's not just any quandle. So an integral quandle ring of a semi-Latin quandle has only trivial idempotence. Like Kaplanowski said that if you have a group which is torsion-free elements, then over a field F, it will only admit trivial idempotence. We made a similar thing, that we have an integral quandle ring with a specific quandle type which is semi-Latin. It will only have trivial idempotence. In particular, we can say that integral quandle ring of a finite Latin quandle has only trivial idempotence. We still were not able to prove this. We worked this out, but we were able to come across a family of quandle rings which gave trivial idempotence. The conjecture is false. This conjecture is false if I replace my Latin quandles with quasi-groups, something which is not Latin. Look at this Cayley table, and we see just by examining that this U is essentially a non-trivial idempotent here. On doing computation, you'll realize that to prove this kind of conjecture, essentially the right distributivity property of a quandle ring is very important. I'm gonna skip, okay. Now we have invariant of knots. Now why are we doing all this? Why are we studying quantals? Why are we looking at its algebraic structure and stuff like that? We essentially are looking at that because we want to talk about knot invariance. We want to look at knot invariance. I want to take my two knots, I want to develop some invariance because my existing invariants are not good enough. One of them is by coloring of a quantal. So essentially you take any two knots, color them using quantals. So at each crossing you just color them off. And then you see how different they are. Doing so, I think I don't have much time, but doing so we realize that coloring with a quantal versus coloring with the set of its idempotents, coloring with the set of its idempotents was an enhancement when we take coloring with a quantal. We went further to realize this question, that a set of idempotents of certain quantals form a quantal themselves, not every, that I already showed. But this brings up to this part, that coloring is an enhancement, coloring with idempotents is an enhancement of coloring with any quantal. Now my question is, taking a 2 co-cycle, can I do the same thing? So a 2 co-cycle essentially is an enhancement over coloring altogether. But instead taking a 2 co-cycle over quantal, how about I take a 2 co-cycle over a idempotence and then color it? I think that would be a better enhancement than the existing enhancement, and that's the current problem that we're working on. With that, I'll end my talk. Thank you for listening. If you have any questions, please feel free.
Any questions for